Good day. For those of you who do not know us, we're the instructional staff for EC 150. Professors Hiren Patel and Werner Dietl and Douglas Harder. In this topic, we're going to look at integer data types. So in this topic, we'll start by reviewing main memory and the fact that we can only store bits, which are actually stored as voltages or potential differences. Then we will consider what we can store with n decimal digits and then n bits. We will then look at the storage of int. We will see that there is a problem with how we store negative numbers. So instead we will start by looking at unsigned types, specifically unsigned char, unsigned short, unsigned int, and unsigned long. And if you're using a Microsoft compiler, unsigned long. We will then do arithmetic with these unsigned integer types. To store negative numbers, we will introduce 2's complement, and we will see that 2's complement is actually very satisfying, and we will look at the 2's complement representation of signed char, short, int, and long. And we will also do some arithmetic with signed integers. Before we can start talking about integers, let's remember that main memory is generally volatile memory where any memory location can be accessed as quickly as any other. Such memory where you can access any entry as quickly as any other is said to be random access, hence RAM, or random access memory. Now, main memory consists of billions and billions of bits. The smallest grouping of bits is a byte, and this consists of 8 bits. So essentially, all of main memory is divided into bytes. A computer with 4 gigabytes of main memory actually has approximately 4.3 billion bytes. This translates to approximately 34 billion bits. Okay, now let's go back to secondary school, even elementary school. Suppose I only allow you to store 3 decimal digits in any number you are storing. Well, in that case, what is the maximum number that you can store with 3 digits? Well, of course, the only numbers you can store with 3 digits are 000, representing 0, and all the way up to 999. This includes 1,000 different numbers you can store with 3 decimal digits. This equals 10 to the 3. Suppose I only allow you to store 3 bits. What is the maximum number of values you can store? Well, if you write them out, you'll notice that we can only write these 8 different numbers. And so, consequently, this equals 2 to the 3. We can only write values from 0 all the way up to 7. Thus, given n decimal digits, it makes sense that we can store 10 to the n different values. And these values are going to range from 0 to 10 to the n minus 1. For example, if n is equal to 10, we could store values between 0 and 9,999,999,999. Given n bits, we can therefore store 2 to the n different values using these n bits. This gives us a range from 0 to 2 to the n minus 1. So for example, again, if n was equal to 10, we could store values between 0 and 2 to the 10 minus 1, which is 1023. Visually, these are the 2 possible extreme values of such a range, all zeros all the way up to all ones. Now, up until now we have been using the data type int Now question, how do we store this on the computer? Well, every local variable or parameter of type int will be occupying 32 bits, and the compiler is going to decide where those 32 bits will exist in main memory. Recall that when stored in binary, a number is just represented by a sequence of ones and zeros, and so therefore on the computer in main memory, it will be potential differences in circuits that are either 0 volts or 5 volts. So again, somewhere in main memory, 4 bytes will be allocated for any local variable or parameter declared to be of type int, and then these 32 bits will be interpreted as an integer data type. So with 32 bits, we could store 32 coefficients of a binary number as we see here. The bit labeled b sub k is the coefficient of 2 to the k in the binary representation. And again, this is why we always start labeling with the 0th bit on the right. Now, the other point is, if we have a small number, say we're storing a value like 1, 2, 10, or even 1000, all the bits to the left of the most significant digit are set to 0. So for example, here we have a program with a local variable m that is initialized with a value 5. Well, somewhere in main memory, 32 contiguous bits are allocated for this local variable m, and in that memory it is initialized with the values where most of the bits are 0 except for the last 3, which are set as 1, 0, and 1 respectively. Now it's important to remember, cout interprets the 32 bits and then prints them as a decimal number when the 5 is printed to the screen. Now we have an interesting problem. How do we store negative numbers? Well, we have to store either a plus or a minus. Well, we only have 2 choices. We can only store something as a bit. And so with a single bit, we can either store a 0 or a 1, or 0 volts or 5 volts. To do this, we could allocate 1 bit to be the sign bit. So let's use that first bit on the left, not to represent the binary number, but rather let's use this to be the sign bit. Our convention will be as follows. If the sign bit is 0, then the number is positive. Otherwise, if the sign bit is 1, this is going to flag the number as being a negative integer. Okay, and again, remember that all of these values are stored on the computer, and so everything is us simply interpreting these voltages that are in a circuit. You're going to again see more of this on your course on digital circuits and digital computers. We're going to go back to storing negative numbers in a bit. However, there was no pun intended there. However, at this point, we're going to consider what happens if we don't need negative numbers instead. We're going to explore this first because this will make exploring negative numbers easier. Now we're going to introduce something called unsigned int. So suppose you have an embedded system that is counting events. If you're counting events, you never need negative numbers. There is a type for this in C++, unsigned int. Note that the compiler interprets these two separate keywords as a single type. The authors of C++ could have used a type such as unsigned underscore int, but instead they chose to add an additional keyword unsigned, and consequently, if the keyword unsigned appears before int, this is a type that is slightly different from int. At this point, all 32 bits of an unsigned int are used for storing a positive integer value. And because there are 32 bits, we can store values between 0 and 2 to the 32 minus 1, or between 0 and approximately 4.3 billion. Now, suppose we have a system where we know in our program we're never going to need values larger than, say, 100 or 1000. This would require no more than 10 bits. So if we use a full int, isn't that going to potentially waste some memory? Actually, in an embedded system, wasted memory can cause significant issues. In a poor design, more memory requires more cost and more power. More power requires larger batteries or reduced battery life. Also, more memory produces more heat, which requires additional cooling. Consequently, there are other integer data types in C++. You can declare a local variable or parameter to be of type unsigned short. In that case, it generally only occupies 2 bytes or 16 bits. That means it can store values between 0 and 2 to the 16 minus 1, or between 0 and 65,535 inclusive. If you need more than 4 billion values, then unsigned long occupies 8 bytes or 64 bits and can therefore store values between 0 and 2 to the 64 minus 1, which is approximately 18.5 quintillion. This is generally sufficient memory for most objects that are being counted. Now, unfortunately, some compilers are peculiar. The C++ standard doesn't require that every single type has exactly a certain amount of memory. Consequently, if you're using Microsoft Visual Studio and you declare something to be of type unsigned long, it's only going to occupy 4 bytes or 32 bits. That's the same as unsigned int, which is a little bit peculiar. If you want a 64-bit integer in Microsoft Visual Studio, you actually have to use the type unsigned long, which is a little peculiar. Now there's one final integer data type that stores only positive numbers, and it is unsigned char. Now wait a second, we've been using char to store a character. Well, it's actually a char, an unsigned char at least, is 1 byte or 8 bits, and this can be used to represent integer values between 0 and 2 to the 8 minus 1, or between 0 and 255. Notice, even if you declare an integer to be of type char, if you do try to print it, it will be printed as a character. Here, for example, I have a for loop where the for loop has a loop variable k declared to be of type unsigned char. Its initial value is 32, and the loop continues until k is equal to 126. It then prints out I am a car and prints K. If we take a look at the output, it's not printing out numbers. Instead, it is printing out characters to the screen. So I guess 32 seems to be a space, 33 is an exclamation mark, 34 is a double quote, 35 is a pound sign, all the way up to 126, which is the tilde symbol. All right, think about that. Now, one thing that you can do is you can check how much memory is allocated for each type on your computer. Here I am using the size of keyword. Now, the size of keyword in C++ represents an operator, not a function call, even though it looks like a function call here. The size of operator is evaluated by the compiler and replaces that keyword and the type with the number of bytes that that byte occupies. So if I was to run this program on my computer using the G++ compiler, my output is as follows. A car occupies 1 byte, a short occupies 2 bytes, an int 4, long 8, and a long is still going to occupy 8 bytes. It does not suddenly occupy 16. All right, so now we've introduced 5 types in C++ that store positive integer values. And in general, unsigned car stores values between 0 and 255, the largest being all ones with 8 ones. Unsigned short allows you to store values between 0 and 2 to the 16 minus 1. And again, the largest unsigned short has 16 ones in it. Unsigned int is generally 32 bits long, allowing us to store values as large as approximately 4 billion. And unsigned long, depending on what machine you're on, is stored in either 32 or 64 bits. If it is 64 bits, this stores up to approximately, well, slightly more than 16 quintillion values. Now, one thing you should be asking is, how does arithmetic work? Because what happens if you make a calculation that is larger than the largest possible value that can be stored in a particular type? So for example, here I have a program where I have 2 unsigned shorts. Now, rather than writing them as numbers, I've written them in binary, and m and n are initialized as shown here. I then print out m and n, and then I add n onto m and print out that sum. As you can see here, m is 33,000 and change, n is 32,000 and change, but m plus n is 395. Now, how did that happen? To see what happened, let's take these 2 binary integers and add them. You should do this yourself just to make sure you understand the concept. However, here is the result. And if you convert this binary number into decimal, you will see that this equals 65,931. However, because we're dealing with unsigned shorts, which are just 2 bytes or 16 bits, we're going to ignore that leading bit, and we're only going to use the 16 least significant bits. That number is 1 plus 2 plus 8 plus 128 plus 256, which is 395, what we saw displayed to the screen. Note that 395 plus 2 to the 16 does indeed equal the expected result. The issue here is that, at least for addition, arithmetic of shorts is performed modulo 2 to the 16. That is, we compute the result, but then we store only the remainder of the result modulo 2 to the 16 for shorts. For integers, we store the remainder modulo 2 to the 32. The same happens with multiplication. Let's take these two numbers and multiply them together. And taking a look at the product, well, the product really doesn't look like it's the product of those two numbers. It's only slightly larger than either one of them. Again, why did this happen? This is the product we are calculating. Now, beyond the scope of this course, but just to give you a hint, this is what happens internally. So we're multiplying the first number by the second. It's just like you learned multiplication in elementary school. We then add all of these up to get the result with the appropriate carries. And now you notice that the product of these two numbers is 1,086,304,934. But we had printed to the screen 45,734. Well, notice that the actual result is equal to a product of 2 to the 16 plus the result we saw, 45,734. Consequently, multiplication 2 is done or performed modulo 2 to the 16 for unsigned short, and it would be equivalently performed modulo 2 to the 32 for unsigned int, and modulo 2 to the 64 for unsigned long. Or if you're using a Microsoft compiler, unsigned long. Now, if adding, subtracting, or multiplying two unsigned integer types and the result is no longer valid, we will say that a carry has occurred. So, for example, if we were to add two unsigned short and the sum is greater than 2 to the 16 minus 1, a carry would have occurred. Similarly, subtracting a larger unsigned short from a smaller one must result in a value that is invalid. For example, 0 minus 1. Also, multiplying two unsigned shorts may produce a product that is also greater than 2 to the 16 minus 1. And again, in this case, we shall say that a carry has occurred. All right, so if we have all these unsigned types that we've been previously discussing, then, well, int is signed. It can store both positive and negative numbers, and so consequently, short, long, and long should also be signed types, and yes, in fact they are. You can actually explicitly use the keyword signed if you want. And it's actually a good idea to use it with car, but for the most part you can leave the keyword signed out. Signed int is the same as int. So how do we deal with negative numbers? As I said before, if the first bit of the number is 1, we will assume the number is negative. Otherwise, the first bit is 0, in which case the number is positive. Now, If the first bit is 0, it's a positive value, and thus the largest positive value that can be stored for each of these 4 types, assuming of course that long is 64 bits, is for a signed car 0 followed by 7 ones, or 127. For short, it is a 0 followed by 15 ones, or approximately 32,000. For an int, it is a 0 followed by 31 ones, or 2 to the 31 minus 1, which is about 2 billion. And a signed long, the largest value it can store is a 0 followed by 63 ones, which is approximately 8 quintillion. As you can see, the largest possible value that can be stored in a signed type is almost exactly half the number of entry values that can be stored in an unsigned type. The only difference being is an unsigned type can only store positive values, where a signed type can store both positive and negative values. Now, why not just use a 1 to indicate a negative number? For example, if 5 is signed to a local variable of type short, it would be stored as a leading 0 indicating that it is positive, followed by a whole bunch of zeros except for the last 3 bits, which would be 101, representing in binary the value 5. In that case, with the convention we just described, a short negative 5 would be stored as that same number, except the leading bit would be 1. First problem. First of all, there are now 2 zeros. 0 and negative 0, because they both represent 0, and we know that negative 0 equals 0. So that's a little bit peculiar. I don't like that. There's a second problem, however, that's much more significant. It's actually really hard to do arithmetic with this convention. So we're going to introduce a different convention for storing negative numbers, one that will allow us to do arithmetic with relative ease. The 2's complement notation is actually significantly better. To store a negative number in a fixed number of bits, take the positive value and to turn it into its corresponding negative number, flip all the bits and add 1. So, calculating the 2's complement, all we do is switch all the bits and add 1. So here we have 5 as a positive short. What we will do is we will flip all the bits, so change every 0 into a 1 and every 1 into a 0, and add 1 to this number. Well, this gives us this value here, so this would be the representation of negative 5. Here's another number. This is equal to 16 plus 32 plus 128, which equals 128, 38, 48, 58, 60, 76, 176. Here's the binary representation of positive 176. If I want to know how to store negative 176, I will flip all the bits and add 1. Well, there's a whole bunch of carries there, but this becomes the representation of negative 176. Now, the smallest negative number is negative 1, so its representation would be as follows. Here we have 1 as a positive integer. Flip all the bits, add 1, and notice that negative 1 is represented by all 1s. On the other hand, the largest possible integer is shown here. The representation of negative this largest integer is, once again, flip all the bits, add 1. So this is the representation of the negated largest possible integer that can be stored in a signed short. If this was a signed integer or just int, we would do the same thing, except we would do it with all 32 bits, and it would only be the first bit that would be either 0 or 1. Now there's an easier way to do the 2's complement as opposed to flipping all the bits and adding 1. Instead, flip all the bits up to, but not including the rightmost 1. So the rightmost 1 and everything after it is shown here in blue. So the 2's complement of this number is all the bits before that 1 flipped. Here's another number. The 2's complement of this number is flipping all the bits up until that last 1. And finally, the 2's complement of this number here is simply this value here, all of the bits being flipped except for all those bits after and including the rightmost 1. The same is true for int. If I wanted to calculate the 2's complement of this number here, I would flip all of the bits up until but not including the rightmost 1. So this is the 2's complement representation of the given number. Same here. I find the rightmost 1 and I flip everything up to but not including that rightmost 1. Now, given a number that is negative, how do we find the absolute value of that number? Well, you just take the 2's complement again. So, for example, what is the value of this int? As before, we flip all of the bits up until the last 1, in which case we see that the absolute value of that number is 101010, and that is, of course, the binary representation of 2 plus 8 plus 32, which is 42. Therefore, the value of the integer that was stored as a whole bunch of ones with 010110 is in fact negative 42. Now, here's a little bit of a quandary. What is the positive value of this negative number, which is a signed short, or just a short? Well, if I flip all the bits up until, but not including the rightmost 1, I get that the 2's complement of this number is itself. Now, what does that essentially mean? That means that this number represents 2 to the 15. Now, if that represents 2 to the 15, then the range of possible values is slightly unbalanced. So for an unsigned car, we can store numbers from as small as negative 128, but only up until positive 127. For unsigned short, we can store numbers as small as negative 2 to the 15, but we can only store positive numbers up to 2 to the 15 minus 1. The same for int, long, and, if you're working on a Microsoft compiler, long. Now, how do you add two signed numbers that are in 2's complement format? For After all, you may be adding a positive number to a negative number or a negative number to a negative number. Well, let's try to find out. Let's just add them as if they were positive unsigned integers. Easy enough, isn't it? So we're just going to perform addition as if the stored representations were unsigned. The processor will just ignore any additional carries. So let us say we have these two signed short values stored in m and n. So the first one is smaller but negative than the second one, and therefore their sum should be positive. And we see that yes, indeed, the sum of these two integers is 395. Now, how did that happen? Well, let's take a look at this. Here we see the first number, which was stored in 2's complement representation, as it was negative, so the leading bit is now 1. And the second, slightly larger integer was positive, and that is second in this sum. If we now add these two numbers together, we have a number of carries, but we're going to ignore the leading one. Therefore, the sum of these two numbers is 11,000,1011, which is 1 plus 2 plus 8 plus 128 plus 256. This equals 395, which is the sum of these two values, as expected. Now let's negate the second number, which was larger. Now we are adding a smaller positive number to a larger negative number, and the result should be negative. And in fact, when we run this program, yes, we see that the output is negative 395. Let's again see how that is done. Now, why did we get this negative result? Well, here we see the first number, which was smaller in absolute value, and it was positive, so the leading bit is 0 and it comes first. The second number was slightly larger, but it was negative. So here we see the second number being stored in 2's complement representation. If we now add these together, here's the result. And we'll notice that in this result, the leading bit is 1. Therefore, this signifies that the number is indeed negative, and to determine its positive value, we have to take the 2's complement of that result. Well, the 2's complement of the sum is the value 11,000,1011, and that, of course, represents the number we see here, which is 395, and thus the sum is negative 395. Now, what happens if we add a number to itself negated? Well, 5 plus negative 5 should equal 0. Let's see if that works. Here, m is assigned the same value as n, but negated. So m is storing the value of n, but it's 2's complement representation. Notice that when we execute this program, the sum is 0. Again, why did that happen? Well, the second number here is the positive value, and the first number is the 2's complement representation of the second value. So here we are adding the negated value of a number onto itself. When we add all these up, notice what happens with the carries. We have a carry absolutely everywhere, and then we have that extra leading one. But that is the 17th bit, and we ignore anything past the 16th bit. So consequently, we see that 31,923 plus negative 31,923 is equal to 0, as expected. Now, if adding or multiplying two signed integer types and the result is no longer valid, we will say that an overflow has occurred, as opposed to the term carry, which was used for unsigned arithmetic. So, for example, adding two positive short and the sum is greater than 2 to the 15 minus 1. Adding two negative short and the sum is less than negative 2 to the 15. Adding a positive and a negative short together can never result in an overflow. Also, multiplying two short and the product is greater than 2 to the 15 minus 1 or less than negative 2 to the 15. If any of these operations occur, we shall say that an overflow has occurred. Now, you're welcome to carry on and examine how fascinating and appropriate the 2's complement representation actually is. It's actually very satisfying. For example, try multiplying two integers that have opposite signs, like 2 times negative 3, where of course negative 3 is stored in its 2's complement representation. You should find that this does indeed result in the 2's complement representation of negative 6. Try multiplying two negative integers like negative 2 and negative 3. When you work this out, you will once again find that the answer will be 110 or positive 6. Also, now subtraction is a lot easier. As you may recall from elementary school, you had to do borrows. However, borrows are tedious because to borrow from the next digit, well, that may be a 0, so you'd have to borrow from the next one and perhaps even the next one, and so on and so forth. And so it's much more difficult to do subtraction the way you learned in elementary school than it is for you to do addition. For addition only requires at most one carry per any one column being summed. So we don't actually have to do subtraction anymore. To calculate a minus b, we just take the 2's complement of b and add to that result, the value of a. Simple enough. And if, of course, b was negative, then a minus b, well, the 2's complement of b would then be positive. Still works. Now, following this lesson, you understand that there are many different types that store integers, including signed char, short, int, and long if you're on a Microsoft compiler. These are stored with normally 1, 2, 4, and 8 bytes respectively. You know that therefore each of these types will store a different range of values, and each of these also has its equivalent unsigned representation, which stores only positive numbers. And because you're using the same number of bits to store positive numbers as you are positive and negative numbers, you can store twice as many values that are positive. You also know that negative numbers are stored using 2's complement, and you know a number is negative if the first bit is equal to 1. You, however, also know and understand that all arithmetic operations occur as if we simply ignore any carries beyond the most significant bit. Here are the references. Acknowledgements the colophon, and a disclaimer. Cheers!